And yesterday I concluded that note each and every precise instrument may not be accurate, right? All precise instrument may not be accurate. See, here you will see this is more precise instrument now. That means each and every time you are getting same result. So this is more precise instrument. What about accuracy? There is less accuracy. I don't have that much accuracy, so you can neglect this one. So all precise instrument may not be accurate, right? And all accurate instruments, so this is more accurate instruments now, 4.5, 4.3, 4.2 may be precise. Definitely the precision is there now, 4, 4, 4, somewhat reproducibility is there. That means all precise instrument may not accurate. This is very very important gate question. All precise instrument may not be accurate, and all accurate instrument may be precise. So that is very very important note we discussed yesterday. Now if you want to define a precision, it is very important concept is this, to find the number of significant figures. I'll clearly explain each and every point how to find the significant figures. Alright, for suppose if you know what is a significant figure means, if pi is equal to it is equal to 3.14, alright, actually pi is equal to 3.14926. That means here number of significant figures is 3. Here number of this is the same pi value. Number of significant figures is 3.1415926536. The number of significant figures increases, that is more precise instrument, right? Definitely those precision will depends on number of significant figures. If a number of significant figures increases, my precision also increases. See how you can find the number of significant figures for a given unknown quantity, right? Just you have to find the number of significant figures, then you will say this, that instrument is more precise instrument or not. For this we have 3 rules, right? So for this, see, for this we have 3 rules. First I will read the rules and I will tell with an example, so with it you can clearly understand, right? Rule number 1, if the decimal point is present or absent, if the given number, yes sir, they will give some number, so with it we'll explain how much precision it is, which one is more precise. So first point, you have to find the number of significant figures, right? In order to find the number of significant figures, we have some rules. There are 3 rules. The first rule, if the decimal point is present or absent, see, this is the rule. If the decimal point is present or absent, the leftmost digit, which is non-zero, is most significant bit, right? I'll clearly explain with an example. First I'll read the things, right? Then go for example, right? If a decimal point means the point value 153.6, so point is nothing but a decimal. If the decimal point is present or absent, the leftmost digit, which is non-zero, we can call it as a most significant bit. Next we'll go for a second point. If the decimal point is absent, the rightmost digit, rightmost digit, which is non-zero, that is my least significant bit, right? If the decimal point is absent, the rightmost digit, which is non-zero, we can call it as a least significant bit. See, I don't have any blackboard, just listen my voice. With an example you can clearly understand, right? And third point, now if the decimal point is present, that rightmost digit either 0 or non-zero, so we can call it as a least significant bit. So there are 3 points you have to remember. The decimal point is present or absent, the leftmost digit, which is non-zero, is my most significant bit. Second point, if the decimal point is present or absent, the rightmost digit, which is non-zero, is my least significant bit. Try to analyze. If the decimal point is present, right, the rightmost digit, which is 0 or non-zero, is my least significant bit. The bits between most significant bit and least significant bit, we can call it as significant digits, right? Okay, I'll clearly explain with an example, right? I'll take an example. Could you remind each and every point, right? See. So my question is 153. In that, how many significant bits? Let me go for our first point. If the decimal point is present or absent, my leftmost digit, which is non-zero, is my most significant bit. Here you can see, is there any decimal point is present? There is no decimal point. The leftmost digit, this is my leftmost digit, which is non-zero, is my most significant bit. So this is my most significant bit. This is my most significant bit. Next, second thing, if the decimal point is absent, here decimal point is absent na, the rightmost bit, which is non-zero, we can call it as a least significant bit. Here decimal point is absent na, the rightmost bit, which is non-zero, is my least significant bit. So this bit, we can call it as a least significant bit. The bits between most significant bit and least significant bit, we can call it as a significant bits. Right? So total, how many number of significant bits? 1, 2, 3. So there are 3 significant bits. So that's the question ends. So you have to find how many number of significant figures. You should follow these rules. Right? Now I'll go for another example. Right? So what is that example? So 153.0. See. Right? 153.0. Right? 153.0. Then you will analyze how many significant. It's not like 153. Directly you won't say the significant figures is 3. Maybe you will get the wrong answer, right? So for this, you have to analyze the first point. If the decimal point is present or absent, my leftmost digit, which is non-zero, is my most significant bit. Here a decimal point is present or absent, nothing, present, no problem. The leftmost digit, which is non-zero, is my most significant bit. So this is my most significant bits, no doubt about that. Right? After that, second point, if my decimal point is absent, the rightmost digit, which is non-zero, is my least significant bit. Here the decimal point is absent na? No, decimal point is present. Then I'll go for a third. If the decimal point is present, the rightmost digit, which is 0 or non-zero, we can call it as a least significant digit. Here the decimal point is present na? Okay. The rightmost digit, which is 0 or non-zero. So definitely here at the 0, definitely you can consider this is my least significant bit. The bits between most significant bit and least significant bit, we can call it as a significant digits. So these are significant digits. So total, how many significant figures? So we are having 4 significant figures. So directly the answer is 4 significant figures. So in this way, you have to calculate for unknown quantity. So if the instrument is precious or not, by calculating the number of significant figures. I'll go for another example, right? I'll go for another example. So what is that example? 0.135. This is very, very important. So with that, I'll conclude this one. See, 0.135. See, 0.135. See, first point, if the decimal point is present or absent, right, the leftmost digit, which is non-zero, is my most significant figure. If the decimal point present or absent, okay, no problem, present, no problem, present or absent. The leftmost digit, which is non-zero, is my most significant bit. the leftmost digit in the 0 కానీ నాకు 0 ఉండకూడదు. The next point, so this is my non-zero point, this is my most significant bit, right? And the second point, if the decimal point is absent, the rightmost digit which is non-zero is my least significant bit. Here the decimal point is absent now, so I don't go for that point. Next point, if the decimal point is present, the rightmost digit which is non-zero is my least significant bit. So decimal point is present, right? The rightmost digit, this is non-zero or non-zero, I don't know, whatever it may be. If it's 0 you can consider also. This is my least significant bit. So between most significant bit and least significant, we can call it as a significant bit. So how many number of bits? There are 3 number of significant figures on the problem. So in this way you have to calculate, so how many significant figures that will exist in the unknown quantity. With that you can easily estimate the precision of the instruments, right? So this is about precision. So precision means reproducibility or consistency in the instrument. We can call it as a more precise instrument. And one more gate point is that all precise instruments may not be accurate, or all accurate instruments may be precise. So that is very very important gate question. And after that, how you can calculate the number of significant figures in unknown quantity. With that you can clearly explain whether the system is more precise or not. If number of significant figures or increases, my instrument is more precise instruments, right? They have three whatever called 3 rules is there. So you have to see the rules and solve the problems also, alright? Next characteristics is linearity. If the system is linear, means output is linearly relationship between output and input. There is a linear relationship between output and input. So then that instrument we can call it as a linear type instruments. That means the linear relationship means, for suppose I have a x-axis, y-axis. For suppose this is input, this is output. X-axis input, y-axis output. So input 2, you'll get the output 4, or else input 4, output also 2 points will change, output also 6. Same, if 2 points increases in input, the 2 points increases in output. So the output is linearly relationship with input. So then we can call it as a linear type instruments, right? Linear type instruments is a desirable or a static, desirable static or undesirable. Definitely this is a desirable characteristic. Each and every instrument should have the linear property, right? And after that, what is the advantage of this linearity in the instrument? Definitely, if the system is linear, means the scale is linear. How linear means the scale is, if the scale is look like the linear scale, if it is 0 and the second one is 2 and always third one is 4, 6, 8, each and every division is 2, linearly varies, right? If the scale is linear, that means uniform scale you will get. If the scale is uniform, you can easily identify the unknown magnitude. But suppose if the scale is like this, you can easily identify the value is 4. If the scale is between 4 and 6, you can easily get whether the 5. So according to the number of divisions, you can easily tell, right? So the scale is uniform, right? If the instrument is having a linear property, means the scale is uniform, and unknown magnitude, unknown value, you can easily detect, right? What is the value of, then we'll go for a non-linear. So non-linear means my output is not linearly varies with the input. For suppose input is 2, output is 4, input is 4, output is 10, input is 5, output is 12. All these things, you don't have any linear relationship between input and output. How the non-linear scale will look like, we'll see. The non-linear scale will be look like this one. If it is 0, if it is 2, it is 10, it is 15, it is 16, it is 25. You don't have any linear relationship. If the pointer plays anywhere, it's very difficult to estimate. That is nothing but some point low it will be high, some point low it will be low. So that means that is a non-linear. So you don't expect these type of characteristics in the instrument. If the non-linear instrument means the scale is non-uniform. the unknown quantity detection is very difficult with the help of non-linear scales. So this is have the figure. This is my ideal line. So this is my ideal line, right? So this is the non-linearity present in the system. So non-linearity. So the difference is nothing but a deviation, right? So how much non-linearity present in the system? So that can be maximum deviation from the ideal line. So this is the ideal line. So this is the ideal line. So this point is going to call it as ideal line. So this is ideal line. So ideal line, right? So this is non-linearity. Non-linearity. So what is the percentage of non-linearity? Maximum deviation. This is a maximum deviation, right? So the maximum deviation from ideal line to the full scale reading, we can call it as a percentage of non-linearity, right? Non-linearity means undesirable condition. You don't expect these type of characteristics in the instrument. So we'll solve one problem on non-linearity or linearity. With that you can clearly understand what is the percentage non-linearity in the system, right? I'll explain in more time. What is a linearity? Linearity means there is a linear relationship between the input and output. We can call it as a linear instrument. Definitely the linear characteristics is a desirable characteristic. So each and every instrument should have these type of characteristics. If the scale is linear, means that we can call it as a uniform scale, right? 0, 2, 4, 6, 8. Each and every division you have a 2, right? Uniform scale. It is very easier to identify the unknown quantity with that scale, right? If it is a non-linear, means output is non-linear with input. If it is input is 2, my output is 4. Okay, input is 4, my output is 10. Input is 6, my output is 24. All these things, you don't have any linear relationship. My scale is non-linear. That means crowded scale. I don't know if it is 0, 2, 10, 24 and all these things. You don't have a number of divisions between these two. So it's very difficult to identify the unknown magnitude. So how we can call it as the percentage of non-linearity? The maximum deviation from the ideal line by full scale reading. We can call it as a percentage of non-linearity. So if you calculate these percentage of non-linearity, you can easily estimate whether the system, whether the instrument which is having a linear relationship or not. Alright, we'll go for one example. With that you can clearly understand what is non-linearity, what is linearity in the instrument. Alright. See, given. So given one system. Alright. So given one system. So input and output characteristics of instrument has given and find out the percentage of non-linearity. My input is 0, output also 0. Right? Input is 5, output is 4. Input is 10, output is 8. Input is 5, 15, 12, 20, 19, 25, 24, 30, 20. Now, percentage of nonlinearity, what is the relationship? Maximum deviation from ideal line by full scale reading. Now, find out the deviations. From 0 to 0, what is the deviation? 0. 5 to 4, what is the deviation? 1. 10 to 8, what is the deviation? 2. 15 to 2, 12, 3. 20 to 19, 1. 25 to 24, 1. 30 to 25, 2. So what is the maximum deviation? This is the maximum deviation. So the maximum deviation 3 by, what is the full scale? Maximum full scale and 30. 3 by 30. So what is that value? So into 100, percentage nonlinearity into 100. So we can call it as a 10%. So that instrument which is having a 10% nonlinearity. That means what is the linearity in that instrument? That is a 90% of the linearity present in the instrument. So that's why we can calculate. So till now we completed